So, what is PVT analysis? PVT analysis is a scientific process used to determine phase behavior and fluid properties of oil and gas samples from the well. The objective is to determine the physical and chemical fluid characteristics to predict the behavior versus pressure and temperature changes. PVT analysis is useful for design of oil production facilities. It is an essential part of exploration and production process. And oil and gas companies have to understand unique behaviors to make data-driven engineering decisions. So what is PVT analysis? PVT analysis is a scientific. The objective of PVT analysis is to stimulate the process that occurs in the reservoir and at the surface during production. And PVT analysis can also provide data needed to correct the prediction of the phase behavior using equation of state, otherwise known as EOS. The objective PVT relationships of reservoir fluids is used to describe how the pressure, volume, and temperature of reservoir fluids are interconnected. And study of crude oil and natural gas properties under varying conditions is used to examine how properties like density, viscosity, and compressibility change with pressure and temperature. And with analysis of fluid phase behavior, it can be used to investigate how fluids exist, such as liquid, gas, or a combination of both, under different conditions. So you might be asking, why is PVT analysis important to reservoir engineering? PVT analysis is very important to accurately characterize reservoirs, including determining the fluid type, e.g. black oil or gas condensate, and distribution within the reservoir itself. And PVT analysis is used to predict fluid behavior during production, such as phase changes and flow patterns, which impact how easily oil and gas can be extracted. And another importance is optimizing recovery strategies to maximize economic returns by selecting the most efficient production methods to use. And it is used for key inputs for simulation models used to forecast reservoir performance and predict future productions. PVT analysis is very essential for essential data, material balance, and reserve estimation, which are critical for field development and planning and economic analysis. So key properties for PVT analysis include bubble point pressure, otherwise known as PB, the pressure at which the first bubble of gas appears in oil. The second is solution gas-oil ratio, otherwise known as RS, the amount of gas dissolved in oil at a specific pressure and temperature. The third is oil formation volume factor, or BO, which is the ratio of the volume of oil at reservoir conditions to the volume at standard conditions. Fourth, gas formation volume factor, otherwise known as BG, the ratio of the volume of gas at reservoir conditions to the volume at standard condition. Fifth, oil and gas viscosity, resistance to flow of oil and gas respectively. And last of all, compressibility, C, the change in volume of a fluid with a change in pressure. Key properties for PVT analysis.
So for the phase behavior, black oil is oil with low initial gas-oil ratio and little shrinkage at the surface. Volatile oil is oil with high initial gas-oil ratio and significant shrinkage at the surface. Gas condensate is a fluid that exists as gas in the reservoir but condenses to liquid at the surface. And dry gas is gas that remains in the gaseous phase at both reservoir and surface conditions. So for the lab test, they comprise of constant composition expansion, which measures changes in fluid volume as pressure decreases at a constant temperature. Differential liberation expansion, which simulates the liberation of gas from oil during reservoir depletion. Constant volume depletion, which measures the amount of gas and liquid phases as pressure declines in a gas condensate system. And lastly, we have separator test, which measures the amount of gas and oil recovered at different separator conditions. So, hi, I'm Daniel Dillon, and I'll be talking about sampling. So, the three sampling methods are downhole or subsurface sampling, which involves a tool that will collect a sample of the fluid in the well under increased pressure. The next one is wellhead sampling, which collects high pressure fluid samples at the wellhead during testing operations. The last one is surface or separator sampling, where these surface samples are collected from test separators. So the three so for sample validation, it includes opening pressures, volume measurement, and free water, or can be called mud checks. Separator oil or liquid bubble point tests at separate condition. Oh, fuck. So for compositional analysis includes spike flash of separator oil, then get the STO density, HTGC and STG-NGA, and separator gas NGA. Sample recombination includes mathematical recombination of flash fractions and separator parameters corrected for lab conditions. Reservoir condition analysis, or called PVT analysis, comprises of constant composition expansion, differential vaporization, constant volume depletion, single and multi-stage separator tests, life viscosity measurements, bubble point and dew point measurement. I think it's So compositional analysis, and these are the machines used in PVT lab.
Hello, my name is Muhammad Skaya. I want to continue about the PVT report analysis. Okay, next. The component, the sample from information, detail about the source of the fluid sample like well, deep, etc. Fluid composition, the chemical makeup of the oil and gas. Lab test result, data and the result from CCE, DLE, and CVD and separator test. Property graphs and table visually representation of PVT properties change with pressure and temperature. The interpretation and discussion analysis of the result, including fluids classification and the data quality. Data validation is checking for the inconsistencies and error in data, ensuring data accuracy and through the quality control measurements and validating lab result with the empirical correlations. Data validation is the interpretation. Fluid characterization is identifying the type of the reservoir fluid. The step is determining the key parameters. Is calculating the bubble point, the oil formation volume factor, or and gas oil volume factor, and etc. and other more important valuable things. Predicting fluid behavior, estimating fluid properties at different conditions. The application is material balance calculation as estimating the original amount of the oil and gas in place. The resurface estimation is determining the amount of the recoverable hydrocarbons, and well performance analysis predicting how well will they produce. The reservoir simulation creating the computer model to predict behavior of reservoir. The
Hi, it's me again. I'll be handling the calculations. So for question A, for the first sample, sample 1013359, we took the data from different liberations and separated tests. We calculated the API, and with that, we input it into the plugin, and we get the bubble point of 2671.999901, which is close to the one in the report. But using the Vasquez and Beggs, we get 2404.092297 psi for both, which is a bit far from what is in the report. For the second sample, We did the same thing, finding the API, taking the data from different liberation and single separated tests. And when we put into the plugin, we get the same bubble point for that is given to us from the report. But with Vasquez and Beggs, it's still slightly a bit different, less accurate, which is, yeah. So for question B, we took the pressure from the CCE experiment. So as you can see, 7,000 until 600, and we put the pressures into the Excel plugin, as you can see with compressibility ABP, and then correlation is where we use manual calculation with the formulas on the right hand side. So there's one formula for when the pressure is above bubble point, and another one for when it is below bubble point. And then we took the compressibility that is stated from the experiment as well. And then we plotted a graph for oil compressibility versus the pressure, right? So as you can see, there's one when it's above bubble point and one where it's below bubble point. And there's a similar trend where as the pressure increases, the compressibility also decreases. So for question C, we took the pressure given to us in the report and we put it into the formula below. And with that, we found the relative oil volume. And then we took that data and we plotted a graph to see where the relative oil volume is at the highest to find the optimum conditions. And for the first sample, sample 101-33559, we see that when pressure is at 2672 psia, oil volume is the highest. So that means that is the optimum condition. For the second sample, we found that when it's at 3086 psia, oil volume is the highest, which means that is the optimum conditions for that sample. So for question C, So for question D, we calculated the relative oil volume for both samples as well as the gas oil ratio for both samples. So and then after that we plotted the graph for both. Uh,
So as a summary, to wrap things up, there are a few key takeaways from our discussion. First, we saw how crucial accurate PVT data is along with a solid understanding of fluid behavior. These are both essential for effective reservoir management. PVT analysis play a major role in field development and production optimization. It's really help drive smarter decision making. Of course, there are few challenges in collecting and interpreting this data, but the good news is, with the right tools and approach, this issue can be managed. Visiting the lab also gave us a valuable insight into the experimental procedure and the equipment involved. It's helped bridge the gap between the theory that we have learned and how it's actually applied in the practice. And finally, continuing to build our skill, especially in advanced modeling technique, will definitely benefit anyone working in this field. Thanks for watching.